That's right. So in the last two classes, we looked at magnetic materials, like different type of magnetic materials, what is the origin of magnetism in magnetic materials, and we looked at applications as well, right? The main important applications. There are many applications. I mean, you can think of so many, any field, there is some form of magnetics involved in that field, be it in biomedical, be it in technician, be it in any field for that matter. But the three main ones were the motors and generators, where permanent magnets are involved, the transformers and inductors, where soft magnetic materials are involved, and then the magnetic data storage, where you have combination of all these materials. Okay, so now we look at a special class of materials or special class of magnetic materials called magnetocaloric materials or magnetoelastic materials. And these are functional materials or smart materials wherein you can apply magnetic field and see changes in other domain, that is in temperature domain, in the above case, in the magnetocaloric case, and in the strain or the stress and strain domain in magnetoelastic materials. Okay, so as the name itself suggests, magnetocaloric means magnetic as well as thermal property materials, right? So we apply magnetic field to change the temperature of these materials. And what do you do by changing the temperature? What is it used for? Any guesses? Why do you want to change the temperature of materials? What are the applications? Where do you need materials where you can change them, where temperature changing is required? Yeah, but so I'm talking about applications. Where is it needed? What is magnetocaloric material? What are magnetocaloric materials used for? Refrigeration, yeah, refrigeration. So, and you can also use them for heating, either heating or refrigeration. Okay, so and what about magnetoelastic materials? So you apply magnetic field and get changes in mechanical properties. In this case, you get strain. So what are they used for? Magnetoelastic. You apply magnetic field and see a change in stress or strain. Strain gauges, you apply, you measure strain from change in resistance. Sorry? Meaning change in dimension? Yeah, so change in dimension, you get change in dimension which is nothing but strain. But how can you make use of it? So the top one is clear, right? You change the temperature, you can use it for cooling or heating, right? So here you change the dimension. So what are they used for? Well, what can you do with that? You change the dimension of a material, and where do you want to use them? Actuators, right? You can actuate something. You apply magnetic field, and it changes the dimension, which is you get some stress from the material because it changed its dimension. Or you can also use them for sensors. The inverse effect also is possible. So if there is change in the dimension of the material, its magnetic properties will change, right? So you can use it to sense strain. So strain gauges are not made of magnetoelastic materials. They are made of resistive materials. You can say strain sensors. Okay? Okay, so those are the materials we'll be looking at now in this class. So now, what is magnetocaloric effect? So it's when you apply a magnetic field on any ferromagnetic material and the temperature changes reversibly, that effect is called magnetocaloric effect. So here you are applying magnetic field through this permanent magnet on this magnetocaloric material, and it heats up. Okay, so that is magnetocaloric effect. And all ferromagnetic materials have some magnetocaloric effect, but only in some you see observable temperature difference. In most of them, the temperature variation is so small that you barely notice it. Okay, so you can use this for either, because it's a reversible process, so you can use it for cooling as well as heating. So how many of you know what's the lowest temperature we can go to? Lowest temperature is what? Minus what? Yeah, minus what? I'm waiting for a number. Minus 4 unit, please. Degrees centigrade, degree Celsius. That's the lowest temperature we can go. Oh, not. I'm not asking, but well, with this material. But what's the lowest temperature you have heard of? So in physics, you might have heard absolute zero, right? Absolute zero is zero what? 0 Kelvin, right? So at that temperature, there is no energy in the material. The volume becomes zero and all those things, right? So, but we, in the lab, go to really low temperature, not 0 Kelvin. So with regular cooling, we can go up to 4 Kelvin, which is minus 269 degrees centigrade. But how do you go from minus 269 degrees centigrade to close to minus 273 degrees centigrade, which is close to absolute zero, which is milli or microkelvin? How do you go to microkelvin from 4 Kelvin? There are different techniques. They're very difficult techniques, very hard techniques. There is, I'm blanking out now, cryo coolers can go up to 4 Kelvin. There is diffusion temperature something. But the most widely used one is adiabatic demagnetization. Okay, so this technique is used to go from 4 Kelvin, that is done with regular normal classical cooling compressors, all the way up to microkelvin. That is done through adiabatic demagnetization. And that is the techniques that are used currently don't use ferromagnetic materials. They use paramagnetic materials. So paramagnetic materials also represent magnetocaloric effect. Okay, so but that's very small. But that small is enough to go, remove heat at such a low temperatures. Okay, so this is this effect was quite well known for low temperature physicists who were working at milli and microkelvin. They were using adiabatic paramagnetic salts to cool down using adiabatic demagnetization. But in 1990 or 94, two scientists from Ames lab, Pichowski and Snyder, they discovered giant magnetocaloric effect at room temperature. So in some class of materials, they discovered caloric effect is quite large, close to room temperature. And those materials are called gadolinium silicides. Okay, so before going to those materials, I want to, so this magnetocaloric effect can be used for magnetic refrigeration or refrigeration. How does it work? So we know that when you apply magnetic field on these materials, it heats up, right? And it's a reversible effect. That means if you take the magnetic field off, the temperature comes down, right? So it's just like your pressure. Boyle's law, right? If you apply pressure on gases and liquids, the temperature goes up, and you cool it down to room temperature, holding the pressure. When it's room temperature, you remove the pressure, it expands, and the temperature goes below the room temperature, right? So the heat is removed here. This is through, the heat is removed here in refrigerators through back fins. Older refrigerators had clear fins at the back, but the newer ones cover it. Okay, so that's how you cool it down to room temperature, holding the pressure. And when you remove the pressure, you go down because it's a reversible effect. Now, if you remove the pressure, the temperature will go down. So from room temperature, it goes down by how much ever it has increased here, right? So you do it again and again, you get cooler and cooler temperatures, okay? So this is how the normal refrigerators work. And just like that, you can use magnetic field as well. So this is magnetocaloric material, apply magnetic field, right? When you apply magnetic field, what happens to a ferromagnetic material? You should know this by now. All spins line up, right? Like here. So when the spins line up, what happens? Spins lining up means entropy is reduced because entropy is degree of randomness. Now randomness is decreased, so entropy is decreased. But if you have to conserve the energy, right? So if the entropy is reduced, so the enthalpy has to go up, which is the temperature goes up. Okay, so that is what happens. So temperature goes up for the material, and now you have applied the magnetic field, the material has become hot. Now you cool it down, just like you did it here in using the fins or a fan or some water circulation, right? When you cool it down to room temperature, holding the magnetic field, now you are at room temperature, and so when you remove the magnetic field, what happens? Its temperature has to reduce by the amount it has increased, right here. So that's what happens. So you cool down below the room temperature. So, and then, yeah, you use it for cooling purposes. And that's how you can use magnetocaloric materials for cooling purposes, either for refrigeration or air conditioning. Okay? So, now, so what's the difference here? The difference is here, pressure is doing the work. Here, magnetic field is doing the work, right? So, but how do you apply pressure on refrigerant? Compressors, right? You use compressors to apply pressure. Whereas here, how do you apply magnetic field? Turn a switch on, right? The current goes through the coils and magnetic field comes out. So compressors work, compressor doing the job versus magnetic field doing the job, right? So here there is a lot of wear and tear. Obviously the efficiency is low of a compressor, whereas here you're not losing any energy just by in the process of switching it on and off. So this is a more efficient process. Okay, so some people even claim that this is almost twice as efficient as that. Sorry, 50% more efficient. Twice would be 100%. 50% more efficient than the um, vapor pressure or liquid vapor refrigeration cycle. Okay, so that's why this gained a lot of attention in early 2000s because it's more efficient and we spend a lot of energy cooling residential and office spaces and also for um, industrial cooling applications. So if we can use this, we can reduce the energy consumption, and if you reduce the energy consumption, you also reduce the carbon footprint, right? So, and it's environmentally friendly because here, what is the refrigeration fluid that on which you apply the pressure? Usually it is chlorofluorocarbon, right? And that is hazardous to ozone layer up. So there is no chlorofluorocarbon here. It's just magnetocaloric material and you circulate water through this, right? Or some benign liquid to extract the heat and to circulate the temperature difference. So that's a schematic of how it works, but you see schematic is so simple, the construction is so complex, right? That's usually the case. So basically this is a permanent magnet. There's a special kind of permanent magnet called Hallback array. So basically you take lots of permanent magnets and you arrange them in a special arrangement with magnetization directions with specific direction. Then, and also here you put some high permeability material. So you get very large field here in the gap. And that is a permanent magnet. You don't need a solenoid or extra electricity to generate magnetic field. You can do it by a Hallback array. It's called Hallback array. And the Hallback array is used in many other applications as well because it can generate much larger field than an individual permanent magnet. Okay, so you use an Hallback array, and this is the magnetocaloric spindle, and you rotate it using a motor. So when it comes below the magnetic field in the Hallback array, it heats up, and then you circulate water through this so that it cools down to room temperature. And when it comes out of here, when it is completely away from the magnetic field, it reduces from room temperature further down to lower temperatures. And then you use it for your cooling purposes. Okay, so and you need a pump to pump water or benign liquid, which can be glycerin or alcohol, anything, to extract this heat here and to keep the cold place cold through circulation here. Okay, so the biggest energy saver is here. Rest all is same as a regular liquid vapor cycle refrigeration, except we are not using a compressor, right? So this saves a lot of energy. That's why it's efficient. And here is a constructed device. And there are several. This was the first one by a company called American Astronautics. I don't know why they decided to make a magnetic refrigerator, but I think they were thinking of space applications. So that company made the first one, and then now there are several labs. We have made one in our lab too, but you have to be very efficient here. When it heats up, you remove all the heat. When it cools down, you have to insulate everything. Then only you can efficiently measure the temperature difference. In our setup, our temperature, theoretically, our temperature difference should have been 5 Kelvin or 5 degrees centigrade, but the measured one is barely 1 degree centigrade because our insulation and timing of the ours is not a spindle. We have a proper reciprocating magnet that goes and applies and comes out. So we have to have time the valves at a very specific timing. So that's why ours is not as efficient as maybe something like this. But ours was built by undergraduate students, so I can't complain. So this is how a magnetocaloric refrigerator works. Okay, any questions so far? Okay, so the magnetocaloric material that we have used or I have worked on is called gadolinium silicon germanium, which is the same material that showed giant magnetocaloric effect for the first time in Ames lab. So I studied the same material. So this material is unique in the sense, you remember we had ferromagnet, diamagnet, and paramagnet. So it undergoes the phase transition, undergoes a phase transition and become paramagnet and ferromagnet, just like them, but with a special additional phenomena. So Curie temperature, I don't think I talked about Curie temperature. So ferromagnetic materials, if you keep heating them, when spins are all oriented in the direction of the magnetic field, those spins will start to gain thermal energy when you start to heat the ferromagnetic material, and eventually the thermal energy will overcome the magnetostatic energy and randomize. And that's when the ferromagnetic material becomes paramagnetic material. So all ferromagnetic materials will become paramagnetic materials at some temperature, and that temperature is called Curie temperature. Okay, so that is Curie temperature or transition temperature. So only the materials spin randomize because of the thermal energy. But here in this material, so the material undergoes a structural phase transition. Okay, so at room temperature, it is a ferromagnet, and at certain temperature, or if you increase the temperature of this material, it becomes paramagnet, and it can also become paramagnet, or if you are in a paramagnet at slightly higher temperature, and if you apply magnetic field, it can become ferromagnet. So what that means is its structure and magnetic phase is coupled. So in this case, at room temperature, this is, I have to see the composition. So I think it's better explained in the phase diagram. I will explain it in the phase diagram, how the phase transition changes the structure as well as the phase. But the material undergoes a structural phase transition. And at that transition, we get this giant magnetocaloric effect. Okay? And the magnetocaloric effect that is so-called giant magnetocaloric effect is measured by delta T of 17 degrees centigrade at an applied field of 5 Tesla. Okay? And at the same transition, you also get a significant change in resistance of the material, which is called the magnetoresistance, which is delta R by R. And that is about 25%. And 25% change in resistance is a large number. Okay? So that means resistance suddenly falls down or goes up by 25% can be easily detected. Okay? And at the same temperature, the material will show a strain of the order of 1%. 1% is a large strain. Okay? So at this phase transition, when material becomes paramagnet from ferro to para, it shows all these effects, which is giant magnetocaloric effect, magnetoresistance, as well as a large strain, which we call callosal magnetostriction or callosal strain. Okay, so which means that phase transition is very important, right? So all these things happen at that phase transition. Whereas in classical materials, the phase transition, at phase transition, none of this, there will be some magnetocaloric effect, but it will not be giant magnetocaloric effect. And there won't be strain. There will be some strain, sorry. There will be some strain, but it won't be callosal strain. This happens because the magnetic phase transition is accompanied by a structural phase transition as well. Okay? So the material not only becomes ferromagnetic to paramagnet, but also it goes from orthorhombic to monoclinic. So it's just orthorhombic is straight structure, right? It's a rectangular structure, and monoclinic means it's just tilted a little bit. So, and that tilt angle is not too large. It's about 5 degrees or something. So, but that small tilt in the crystal generates 1% strain. Okay, so this is a special kind of magnetic phase transition because there is crystal structure change in it, and they're both coupled. Okay, so and these properties are quite large, and that those can be used for. So if there is a strain, that means it can be used as an actuator or a sensor. If there is magnetoresistance change, it can be used as a sensor, right, to sense change in resistance. So here is the phase diagram of this material. So on y-axis is the transition temperature, means it's a temperature at which the material changes its magnetic or structural phase. And on x-axis, we have composition of silicon and germanium. Okay, gadolinium phi is fixed, and we are substituting here germanium with silicon. And as we keep substituting, the transition temperature increases. Okay, so when it's purely gadolinium phi, germanium 4, the transition occurs at 50 Kelvin. That means at room temperature, it's a paramagnetic material. Okay, so this is paramagnetic and this is ferromagnetic. And as you start to increase the composition of silicon, this is an alloy. Okay, so no, sorry, this is not an alloy. This is substitutional. So we are substituting germanium with silicon. So it's still a well, you can call it an alloy, but it's gadolinium. Now we can, when we start to substitute germanium, it becomes gadolinium, silicon germanium, depending on whatever is your silicon content. Okay, so at this composition at about x equals 2, so at x equals 2, if you substitute x2 in this one, silicon 2, 1, so x is not equal to 2. This is x equals 0.5. So just let me check. So this is, sorry, this is silicon content. So it becomes, this is gadolinium 5, silicon 2, germanium 2. At this composition, the transition is close to room temperature. Okay, it's not quite room temperature, but it's close to room temperature. And at this temperature, the phase transition occurs from monoclinic paramagnet to orthorhombic ferromagnet, or vice versa. Okay, so but when you add more silicon, you are into this region where there is phase transition, but this phase transition is not accompanied by a structural phase transition. Okay, what that means is here the crystal structure doesn't change. It's orthorhombic crystal. Here is also orthorhombic crystal. Just the magnetic phase changes here. Okay, so here you have magnetic phase change as well as crystal phase change or crystal structure change. That means in this region you get all those interesting properties, that is giant magnetocaloric effect and magnetoresistance as well as colossal magnetostriction. Okay, that is 1% magnetostriction. That's because there is crystal structure change as well as magnetic phase change. Okay, so this is our point of interest, because this is what we want to explore and utilize these interesting effects, including giant magnetocaloric effect and colossal magnetostriction. Okay, so any questions about this? So yeah, the other thing is when you have just magnetic phase transition, we call it second order phase transition. When there is structural as well as magnetic phase transition, this is a first order phase transition because the changes here are abrupt and you see interesting property changes at first order phase transition. And this is slightly more complicated. There is antiferromagnetic phase as well here. So we'll leave that for now. Okay. So, and it's also at very low temperature. We rarely go down to 100 Kelvin. 100 Kelvin is about minus 173 degrees centigrade, right? So we leave this and we are interested in here, maybe some of it here, because this is a ferromagnetic material here, right? So, but this is our primary region of interest. And here is one composition. It's not quite 2. Okay, this is not 2 here, it's 1.8. 1.8 means you are slightly closer here. Okay, if you are here, the transition is about below 250 or around 250, right? Yeah, it's below 250, 240 Kelvin. Okay, so we are 1.8 is here, and that is 240 Kelvin is the transition temperature. So what that means is you take a material, this composition material, At room temperature, it's paramagnetic. There is no magnetization here, right? And you start to decrease the temperature, and as you go close to 240, it suddenly jumps to very high magnetization and stays in that one. Actually, there will be slight increase in magnetization, but because this jump is so large, this slight increase you don't see. Okay, so it becomes, this is ferromagnet here, this is paramagnet here, and this transition is called magnetic phase transition, and this temperature is called Curie temperature. But in here there is structural phase as well, so this is called first order phase transition. Right, so this is a modified phase diagram. This is kind of my bragging slide, wherein I worked on so many compositions and updated the phase diagram of this. The previous phase diagram was done by many researchers. These all compositions and these lines were determined by several researchers, mainly from Ames lab. But when I worked on all these compositions, so if you look here, so again, I don't want to overcomplicate things. So here it's second order phase transition, right? So there is no structural change here. So paramagnet becomes ferromagnet, the crystal structure remains the same. Here, crystal structure changes, hence the magnetic phase changes, hence it becomes paramagnet, or ferro to para or para to ferro, right? So what if the crystal did not change its structure? What if we retain the crystal structure same as, so for example, we are going from low temperature to high temperature, and we come here, we don't get a crystal structure change, we retain the crystal structure. What will happen to the magnetic phase? It should retain the same phase, right? Because it will not become paramagnet because the crystal structure hasn't changed. So if the crystal structure doesn't change, it will have a Curie temperature at a later temperature. And that one you can only calculate, okay? But you can't see experimentally, because as soon as you reach that temperature, the crystal structure changes to a new crystal structure, and new crystal structure is a paramagnetic phase. Okay, so that's why we say this became paramagnet. Actually, it did not become paramagnet. It changed its crystal structure. The other crystal is a paramagnet at that temperature. Okay, so if you calculate its, what would be its expected transition temperature, that falls here. Okay, so when you do for all these materials, you get another line, and this line is a projected second order phase transition, which is an imaginary line. And likewise, you can do the projected second order phase transition for these samples down here. And that's what I have done and updated this phase diagram. So this is, again, a lot of material science. It's whether it has any practical applications, I don't know for now, but maybe later on. Sorry. Okay, so now that is, we were looking at the phase diagram, right? Now let's look at the magnetoresistance, or let's measure its resistivity. So here is an example. This is a unique material that this phenomena doesn't occur in all the magnetic materials. Okay, because the structural and magnetic transitions are coupled, so you get these interesting properties. So now, for this composition again, if we measure its resistivity, right? So we start from room temperature and start to cool it down, and it's paramagnet all the way until 240, and suddenly it becomes ferromagnet. So that means its crystal structure from monoclinic becomes orthorhombic. And monoclinic crystal structure has a lower resistivity, and suddenly it changes its resistivity to higher resistivity, and this becomes ferromagnet. Okay, but if you remove the field, or if you start to heat up, it should follow the same line, but that doesn't happen here. This, in fact, mirror images the other one, and the resistivity keeps increasing, and especially when there is sudden strain, volume change, resistivity jumps. Whereas it should have actually come back here, right? But we see that when you cycle this material through this phase transition, to the structural transition, resistivity of this material keeps increasing. Do you know why? Can anyone tell me why that might happen? So when the crystal structure from orthorhombic to monoclinic, you make a phase transition, change the crystal structure several times, it undergoes large strain, right? 1% strain. So what happens when you cycle a material through large strain? Sorry? Hysteresis? No, but if you cycle it through large strain, not through magnetic field. Well, so yeah, strain hardening. What happens in strain hardening? Fatigue failure will happen, but why fatigue failure will happen? Microstructure. What are the microstructures? That's correct answer, but I'm interested in resistivity, right? So they're related. What you're saying is right, but that's not giving me an answer there. So what happens? You start to introduce dislocations, right? So you start to introduce microcracks and dislocations. And what happens if you introduce microcracks and dislocations in a material through to its conductivity or resistivity? Increases, right? Because the electrons have to travel. Their electron transport has to take place in order to have a conductivity. And if the mean free path of the electron is longer, then so it will be longer because there are so many dislocations and microcracks. So the mean free path of the electron becomes longer. So the resistivity increases, the conductivity decreases. Okay, so dislocations and microcracks will increase the material's resistivity, and that's what has happened here. Instead of me seeing resistivity coming down, because I was expecting that I will see a transition come back and follow the same path, but that did not happen. And when I cycled several times, it kept going up. But this behavior did not stay, meaning exact mirror image did not happen at later cycles. Okay? So if you plot number of cycles versus resistivity, you see this continuous increase. And it may saturate after a while when you have enough dislocations. So, and also in magnetic properties, what happens if dislocations increase? Think of domains. If you have dislocations, what happens to domains or domain motion? They're pinned, right? So what happens to the magnetization curve? The coercivity increases, right? So that's what we see. The coercivity starts increasing after you cycles through several cycles. So that means you may make it as a magnetocaloric material, but it will deteriorate. It will deteriorate after about few cycles. So you need to have a mechanism to improve the property after certain cycles. Okay, so that's something that I observed during my study. So again, when you are a PhD student, when you want to describe any new mechanism, you not only just show the results, but you build a model around it. Okay, you have to theoretically explain, quantify it, and explain the underlying mechanisms and come up with a model. Model means basically an analytical expression to quantify how that happens. Okay, so we had to explain this, why this continuous increase in resistance happening. Okay, so now what we know about dislocations and resistance and all that, so it is governed by a law called Mathesian's law, which says that the resistivity of a material is a combination of resistivity of the lattice plus the resistivity of the dislocations plus the resistivity of microstructure. And also, we know Arrhenius equation. Arrhenius equation is usually for chemical reactions. So in Arrhenius equations, you can, again, this is when this is shows, this expression shows what happens to the number of dislocations over a certain time at given temperature. Okay, so we wanted to see what will happen if you increase the dislocations to certain amount and keep it aside at a certain temperature for a certain time. Okay, this Arrhenius equation, based on this Arrhenius equation, there will be change in the number of dislocations over time, which is in this case will come down because dislocations will combine and annihilate. Okay, so this is like a chemical kinematics equation. So here N naught is again the ground level dislocation density, S is Arrhenius constant, delta is the energy required for a dislocation to overcome the barrier at temperature, certain temperature, and at certain temperature. And these are all parameters that can be determined from the literature. So now I can see what happens to this number of dislocations over a certain time when I keep it at certain temperature. Okay, so now this part I can substitute with these dislocations, right? But this is with a constant because the resistivity is proportional to number of dislocations. So I use a constant to make this as a resistivity due to dislocations. And my lattice and microstructure will remain the same because I'm not changing anything there. So this is how we, yeah. So yeah, Kb is Boltzmann constant. This one? This is K is a proportionality constant for if you have so many number of dislocations, how dislocations scale to a given resistivity. Yeah, that depends on, that's a material dependent parameter. Yeah, different material. This is for pure, this is silicon we used a silicon value there. So K, delta E, S, and naught, these are all constant parameters we dig out from literature for a given material. Okay, so now when you combine this should be my resistivity, and that these are again resistivities that are constant. This is the only resistivity that's changing. So now if I presume this as two constants and plot them for different time at different temperatures. So if I hold the material after cycling it, hold the material at different temperatures, over time they will decrease like this. The resistivity will decrease like this. Okay, so this is theoretical prediction based on the model we built. Okay, so this is how you build a model to explain your experimental results. Okay, that is required in when you do PhD and publish a paper for a new phenomena. Otherwise, you can't explain what's happening. So if you can't explain your results, it's difficult to publish them. Sometimes you can publish. You can say, we don't know what's happening. This is very interesting. This can be useful. But usually you build a model to explain it. Okay, so this is how we explained it. This is the theoretical prediction, how the resistivity will decrease for the material at different temperature after we cycle it. Okay, so, and I keep doing it that side. So this is what we found out when we measured for this single crystal sample. And after certain cycles, I don't remember what were the number of cycles. Yeah, I don't remember now. This was way back in 2010. Well, we published in 2010. We did it in 2009. So you cycle over several times, your resistivity increases, and now you hold it at this temperature, 345, for 50 hours, and you constantly measure the resistivity, and these are the measured, and that's the red line is the predicted from our previous equation, from the model. Okay, so here are the constants we used. There is a sudden change in the topic here. Yeah. This spike. Okay. Yeah. So when you're measuring experimentally, you can have experimental errors, but the broad behavior, and we also don't know why there is more pronounced decay at that time range. Okay, so that's how the mechanical, which is dislocations, are affecting the electrical properties, which is resistivity, which is obtained by applying magnetic field and changing the phase transition. Okay, so that is this material behavior. So although this may not be a very good material for magnetocaloric refrigerator, because it undergoes a large strain change, which can introduce dislocations, and its performance may reduce, but it has interesting properties nevertheless. Okay, so that's about any questions about magnetocaloric material or first order phase transition material? This one. No? Okay, let's move on then. So not all magnetic materials behave like this. This is, as I said, special class of material called giant magnetocaloric material. And now let's move on to what is called magnetoelastic materials. Okay, so let me remember why I. So yeah, magnetoelastic materials we talked about, right? They talked about them, right? So they are used for getting a strain when you apply a magnetic field. You can also get strain with magnetocaloric material, but there you are getting strain because the material undergoes a structural phase transition, right? It goes from one crystal structure, monoclinic, to orthorhombic. Hence, we get a colossal strain. But these magnetoelastic materials are slightly different. They don't undergo first order phase transition, which means they don't change their crystal structure, but they change their dimension when you apply magnetic field. And those are called magnetoelastic materials. And that the inverse is also true, which means if you apply a strain on these materials, its magnetization changes. That means you put a material and stress it, and if you have a secondary coil or winding, I talked about primary winding and secondary winding, you remember? The primary is for applying magnetic field, secondary is for detecting the magnetic field, right? So if you put a secondary winding, just a copper winding, nothing more, just a copper winding, and connect it to a voltmeter, and if there is any magnetization change or induction change, the copper winding will sense a voltage, and that you can read, right? So that means if you have a magnetoelastic material on any structure, and if there is a strain on that structure, and the magnetization changes because of the magnetoelastic effect, and that magnetization change can be sensed through secondary winding or secondary coil, right? So that's how you can measure or sense strain change through magnetoelastic materials. And that can be used for health monitoring or structural health monitoring, health meaning structural health monitoring of bridges and aircraft. Okay, so if you can do that efficiently, then you can actually avoid disasters like bridge collapses, or you can say you can also use strain gauges to do the same. But you know, strain gauges are so unreliable, right? Because there is small change in temperature will give significant change in the resistance of the strain gauges. Whereas with magnetoelastic materials, you can actually sense the change in magnetization, which is related to change in the strain of the material where it is. Of course, you have to mount a magnetoelastic material on the structure, and the strain on the structure has to transfer through the magnetoelastic material. So you have to, just like how you mount strain gauges. So are you familiar with strain gauge mounting procedure? Yeah. So strain gauges have to sense the same amount of strain, which means there should not be any air bubble, and so on and so forth, right? Same thing applies here, okay? So that means magnetoelastic materials can be used for structural health monitoring in examples such as bridges or aircrafts. So magnetoelastic effect is also called magnetostriction. Okay, so the magnetostriction is the definition of magnetostriction is the property of magnetic material to change in its dimension when you apply a magnetic field. Okay, that is, or when there is change in magnetization. So how does it happen? So this is not structural phase transition. You're not seeing any crystal structure changes here. So when you apply magnet, this is your magnetic material when there is, it's a ferromagnetic material, will look like this when you don't apply any magnetic field, right? So these are domains. So now if I apply a magnetic field, oh, battery is running low. I think should have lasted longer. Okay. Do you see? So when you apply magnetic field, you are applying magnetic field in this direction. Then now you have one domain. So multiple domains become one domain. And what happens to the size of the material? It increases, right? Because when all the domains align like this, the material also changes its dimension. And that is magnetostriction. Okay? Any questions here? You know how domains all, as you apply magnetic field, domains start to align. There will be domain motion. And of course, if you have pinning sites there, dislocations and defects, it's difficult. So which means you can have higher strain, or you can obtain strain with lower magnetic field if your material is purer or if it's single crystal. Okay? Does that make sense? So the domain alignment changes the dimension of the material, and that is what is called magnetostriction. So now you can use it as an actuator, because by applying the magnetic field, the material expands and you get an actuation. So can anyone guess what might be the strain that you get for, say, an applied field of 1 Tesla? In terms of ppm. Of course, it's not. So 10,000 ppm is 1% strain, right? So parts per million. So 10,000 parts per million makes it 1%. So the strain here is of the order of about 500 ppm. Okay. So the magnetostriction magnetostriction material can be used as actuators, but the actuation length will not be too long. Okay. So and then you can also use it the other way around, which is reverse magnetostriction, wherein you apply a stress on a magnetostrictive material or a magnetoelastic material, and you see a change in magnetization, and that can be sensed by a secondary winding, which is, or a sensor. There are also other sensors. Secondary windings are crude sensors. There are semiconductor sensors, which are Hall effect sensors, and Hall effect sensors are more sensitive. Okay. And actually, the reverse effect is not magnetostriction. It's called Willery effect. Okay, named after a guy by name Willery's last name. So it can be used for structural health monitoring, as we talked about. So what are the desired properties of these magnetoelastic materials or magnetoelastic sensors? If you want to sense the strain in a structure, what should be the desired properties of these materials or these sensors? There's one thing that we all know, right? Linearity. What that means is if I apply certain stress, I should get certain change in magnetization, and that should be linear. Right? If it is linear like this, it's easy to determine. But if it has some complex shape like this, you have to use some complex analytical expression, which might make it harder to predict or calculate. Okay, so linearity, and the other property is you should not have hysteresis. It should be unhysteretic, meaning it should not have this coercivity. Okay, it should be, there should not be any gap in between the two curves. So no coercivity. And it should, of course, have high magnetostriction so that there will be high change in the magnetization, which is also means high sensitivity, that is delta lambda is here. Lambda is nothing but the deformation by delta H, meaning for small applied field, you should get large deformation. So that means you have to have high magnetostriction. So that's high sensitivity, high magnetostriction. So these are the desired properties for magnetostrictive sensors, and they are very, if you have all these properties, they can be adopted for structural health monitoring, both for bridges as well as aircrafts, ships, and so on and so forth. So the materials, now let's come to, we talked about all without specifying what exact material, right? So the first material that showed high magnetostriction was a material called terphenol D. This was produced by US Naval Research Lab. Terphenol D stands for Terbium Iron Naval Ordnance Laboratory. Okay, so they came up with that. So terbium and iron, when they made a binary material, they saw large magnetostriction, and they named Naval Ordnance Lab because Naval Research Lab was Naval Ordnance Lab before. So they are, and D stands for, I don't remember now. I knew at one point. So that is terphenol and iron alloy that has high magnetostriction. And again, any ferromagnetic material has to show some magnetostriction, right? But we want really high magnetostriction so that where the reverse effect has to show large magnetization change. And cobalt ferrite is another material which has high sensitivity, meaning you apply small magnetic field, it shows large magnetostriction. But the saturation magnetostriction is large in terphenol D. And chemical substitution can change the properties. So yeah, again, we are repeating the same thing. So you don't want hysteresis, you want unhysteretic, meaning there is no hysteresis in the response. So yeah, sensitivity and range of operation. Okay, sensitivity meaning, so this is a magnetostriction curve. So this is ppm, is parts per million strain, and this is applied magnetic field. So the material starts to show negative strain, meaning it compresses, it becomes smaller. This is for this material. This is cobalt ferrite that shows negative magnetostriction. Other materials show positive magnetostriction. And so the sensitivity meaning, if you apply small magnetic field, you should get large strain. So that means the red line is has higher sensitivity than the black line. So, and also red one has large sensitivity. So, which means the range of operation is higher in the red line, as well as its sensitivity is higher. Okay, so but some materials could be sensitive, but they saturate at lower strain values, then your operating range is lower. Okay, so in this case, the red line has both high operating range as well as higher sensitivity. Okay, so and again, how do you measure sensitivity? You take H0 by H2. Again, I don't remember. This was a long time ago when we worked on this. So, but you get the idea. Sensitivity means at a given magnetic field, or with a small applied magnetic field, you should get a large magnetostriction. Okay, so cobalt ferrite is a substitute for terphenol D. Terphenol is again terbium and iron. Terbium being expensive material, it's a critical material. It's one of the rare earth materials. Terbium has high range, but it has low sensitivity, whereas cobalt ferrite is somewhat inexpensive material, and it has higher sensitivity and slightly lower range compared to terphenol. So again, in my advisor's lab, there was a lot of work done on how to improve the sensitivity by substituting iron with germanium, or cobalt with germanium, and cobalt with manganese, chromium, gallium. They tried all sort of ethyl-methyl chemistry, basically substituting something with something and looking for better sensitivity in this material. And they finally came up with a material that is, I think, chromium substituted cobalt ferrite. I think had showed the highest sensitivity, and that was the conclusion. That was a systematic study by substituting many materials to determine high sensitivity magnetostrictive materials. Okay, so this is again how they obtained cobalt and germanium substitution. I don't want to go too deep into exchange interactions and anisotropy, but basically by substituting, what you are doing is you are changing how two elements are coupled magnetically. That is, by this is a new term for you, that is exchange interaction. But just think that it's a magnetic coupling between two atoms in a crystal lattice. Okay, and anisotropy we have discussed. We can change the anisotropy again by when you substitute a material that changes the lattice parameters, then you can change the anisotropy as well. The lattice parameters can change anisotropy not just because of the dimension change, but also because of what is called a spin orbit coupling. Again, that's a slightly more complex phenomena, but what you need to know is when you substitute, a lot of things can happen in the lattice related to magnetic exchange or magnetic coupling that will change the sensitivity, or that will change how much they will expand when you apply a magnetic field. Okay. So you want higher range, lower power consumption, less hysteresis, which is a good candidate for, and here is different lambda max, which is the range, and here is the sensitivity. And the most sensitive is the gallium substituted cobalt ferrite, but it has slightly lower range. It has lower range than the germanium substituted cobalt ferrite. The germanium has lower sensitivity. So you have to play with different substitution to get the desired property. Sometimes you may not care about the sensitivity. You may think you may have large or you might have access to energy, inexpensive energy, in that case, you are okay to apply large magnetic fields, but you care about the range. So 3:30, I think we finished a few minutes early. We started 10 minutes late, so we finished 10 minutes early. I think I'll take that for question and answers. So that's my last slide. These are references. Um, of course, there is one more slide for my contact details. So any questions so far? If you don't have questions, I will ask you questions. Yeah. No. So what are the other ways of measuring strain? Come on, you are mechanical engineers. Please don't disappoint us. So you know how to measure strain, right? How do you measure strain? Strain gauge. We just talked about strain gauge, right? What are the other ways? Yeah, LVDT is another one. Linear varying differential transformer, LVDT, right? Yeah, so there are many ways, right? So what are other materials that show change in dimension when you apply a current or a magnetic field? We have discussed, it's not like, these are new questions. I've talked about this in last two classes before. Which are the other materials that will change dimension or show strain when you apply electric or magnetic field? Sorry? How will they show strain when you apply current? All the conductors. Some conductors do not show. Why will conductors, electrical conductors, show change in strain when you apply a current? No, right? If you apply temperature, maybe, yeah, because most of the metals will have some coefficient of thermal expansion, so they may increase, but not current. Piezoelectric materials. We talked about piezoelectric materials, right? Quartz, shape memory alloy, nitinol. So shape memory alloy, SMA. That is our professor here. His initial is also SMA. So yeah, I call his shape memory alloy. And he's an expert in that field. He has done 3D, 4D printing of shape memory alloy. So shape memory alloy also shows, right? Okay, so you don't have any questions for me? Yeah. Sorry? Oh, yeah, sure. Yeah. Mm-hmm. Secure, okay, secure in what sense? Because secure, so if you're talking of retrieving the data is not lost immediately when there is some damage, because the magnetization is written into the magnetic domains, so the domains stay that way, and the retention of that information is very robust. So it retains that information for many, many years. Whereas in ST, the way you change the resistivity state, right? You make that domain or small um, area, either high resistive or low resistive, by using a floating gate method is not that robust, meaning small change in the stress or temperature can move the charges between the gate. So that is not as um, stable as a magnetic domain. That's why it's more secure, in the sense it's more safe or reliable to store data in hard disk than SSD. But SSD, sorry? Yeah, for the same amount of data. Yeah, yeah, so that's a good question. But so it's just to do with how you make. So in hard disk, how we make a magnetic material, magnetic plate, and we magnetize a small domain, right? And to make that domain, we're not doing anything special. We just make sure that our grains are smaller, right? In case of an SSD, you are dealing with a transistor. You're making a transistor. Each transistor is 1 bit. Okay, so the floating gate there, which you control the resistivity state in SSD, that is by each transistor, and making that transistor is by lithography. So lithography is expensive, making you need lots of masks and lots of nanofabrication processes, and that's why it's expensive to make a SSD for a certain. So, but I mean, research meaning it's we have to come up with ideas, right? But this is completely different. It's transistor based, it's magnetic based. How are you going to merge them together? So SSD also is faster because the way you retrieve the data and write the data is very quick compared to, because in magnetic this it spins and you have to come back to the same, it has to come back before you write it, right? Whereas SSD works with just, it has a certain architecture. You send the current and you know which location. So if you want to make SSD more robust, that means you have to change the way you pump the charges through the gate, which is, I don't know, there might be ways, but they might not be that easy to do. Okay. Yeah. Yeah. Huh? Yeah. Mm-hmm. Volumetric. So yeah, I think that's a good question. Frankly speaking, I don't have an answer because the NDT mechanism is, I mean, it depends on how you make it, right? It's not, there is no robust device. It's just a primary coil and a secondary coil, right? So depending on orientation of your secondary coil, how you sense the flux and how you apply the flux. So depending on the orientation of your magnetic field from the primary coil, you may have high efficacy in determining some cracks aligned to this magnetic field as opposed to other orientations. Okay, those are good questions.
Since you started asking questions, now they got the.
Yeah. So right, I think it's 3:40, so that's time for a break. So let's go for a tea break. Thank you.